Chapter 6, Waves. The stormy sea is one of the awesome demonstrations of the power of nature. Waves crash on the coast with enough energy to turn over cars and destroy buildings. But how is such energy transferred from the deep sea where waves are generated? In Form 1, we defined wave as a disturbance propagated through medium or space. Waves can be transverse or longitudinal, depending on the displacement of particles with respect to the direction of propagation. In this chapter, we shall look at water waves, light waves, and sound waves, and see their behavior and what that means. Water waves and light waves are transverse, but sound waves are longitudinal. Important to remember is that waves only transfer energy, not matter. When the vibrator in a repo tank is turned on, you can see the cylindrical pedal oscillates and that drives the surface of the water up and down to create parallel waves that travel along the tank in this direction. To actually look at a single wave crest as it moves along the tank is rather difficult, so we have a diagram that shows it. The wavy line represents the surface of the water as we look from side, and the height has been exaggerated. This is the profile of the wave and it's moving to the right at a constant speed. If we freeze the motion, you can see three wave crests and troughs between them. The amplitude is defined as the maximum displacement of the water surface from its main position. We can also use this static picture of the wave to define its wavelength. This is the horizontal distance between two successive crests or two successive troughs. Wavelength is represented by the Greek letter lambda. In fact, you can think of this snapshot of a wave as a graph showing the vertical displacement of the wave as a function of distance at a particular instance of time. If we look at the waves moving, you can see the wavelength is the distance between two successive crests. So when a bar is attached to the vibrator, plane waves are produced. Circular waves can be produced by attaching a pointed end to the vibrator. And so when a wave is generated, it's propagated through medium and takes time to travel. So wave carries energy but only to certain speed, and this speed depends on what kind of wave that is and the medium of travel. So light waves travel fastest and we use it to see the rock hit the water surface. Sound follows much slower than light and we use it to hear the splash the sound makes as it hits the water. Both of these waves travel faster than water waves. This is why we see the rock hit the water slightly before we hear the splash, and why we are aware of the sight and sound of this before we feel the waves that are produced. When waves like sound waves travel through a medium and strikes the surface of another medium, it bounces back to the original medium. When this rope is used to generate a transverse wave, the wave travels and hits the fixed point and starts another journey back. Thus, waves suffer reflection and obey all the laws of reflection. So the angle of incidence is equal to the angle of reflection. Also, the incident wave, the reflected wave, and the normal at the point of incidence all lie on the same plane. Reflection of sound is vividly experienced in echoes. Reflection of light waves is obvious when light strikes a shiny smooth surface like a mirror. Refraction. Refraction occurs when the waves move from one medium to another. And again, it doesn't matter whether it's water, sound, or light waves. For example, it occurs when water waves move from a deeper to a shallow water region and vice versa. Back to the ripple tank, the dipper is used to send parallel waves across the ripple tank. Putting a plastic sheet in the water makes this part of the tank shallower than the rest. Waves travel more slowly in shallow water. This change in speed changes the wavelength. The wavelength on the top is shorter than that at the bottom. When the sheet is at an angle, the wave also changes direction. The wavefront bend as they reach the plastic sheet. Shining a powerful light source through a thin slit produces a straight, narrow beam. Place a glass block in its path and the beam starts to behave differently as the block is rotated. Some of the light is reflected, some passes into the glass. The light bends in one direction as it enters the block and in the other as it leaves. This bending of light is due to the change in speed of the light waves as it enters and leaves the glass at an angle. Diffraction of waves. Now let's look at what happens to water waves as they pass through an aperture. We put an aperture here, but it's rather too wide for the purpose we need it. So let me place this to reduce the size of the aperture. And now if you look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of waves as it passes through an aperture is known as diffraction, and it's a property of all types of waves. What do you think would happen if I made the aperture smaller? It would surprise you that a narrower aperture leads to more spreading out of waves, more diffraction. If instead I made the aperture wider, you can see the waves become less spread out. Diffraction is less pronounced. Suppose I change the frequency of the wave. If I make the wavelength longer, you can see the waves become more spread out, more diffraction. And if I made the wavelength smaller again, and even smaller wavelength, then there's less diffraction. So diffraction is pronounced if the aperture is made narrower or the wavelength is increased, and is less pronounced if the aperture is made wider or the wavelength is reduced. In fact, all kinds of waves exhibit diffraction through an aperture as long as the aperture is not too wide. Even circular waves. Consider this ripple tank arrangement. The tip of the needle connects the tip of the vibrator and produces circular waves. These wavefronts will be traveling in the direction along P. Two glass plates X and Y are immersed in the tank are far from the tip such that there is a gap between them. The wavefront will be incident to XY, acting as an obstacle with an opening which we refer to as an aperture. You would think that only some waves will pass through the aperture AB, but we shall have a different situation. The circular waves which pass through AB results in a higher number of wavefronts which are circular in nature and will be spread out in all directions. The waves emerging from the aperture AB will deviate from the original path P and will travel in the directions such as Q and R. How about light waves? The wavelength of light waves are similar to the wavelength of water waves when compared to each other and to the wavelength of the sound waves. Therefore, diffraction of light requires very small apertures. The bending of light waves around obstacles whose dimensions are comparable to the wavelength of the light which is incident and hence spreading to shadow is called diffraction. Let's see the diffraction at a straight edge. We place a half scale in the ripple tank such that its length is incident with the water surface, but the width is perpendicular to the surface. This type of an obstacle is called a straight edge. Here A, the tip of the vibrating needle, behaves as a source of circular waves, which spread out and travel towards scale BD. The waves spread out equally in all directions until they reach BD. At this point, the lower edge of the wavefront is cut off completely. Only the upper portion beyond the straight edge should travel beyond the scale. But sometimes there are weak waves that are spread out into the lower region. So one of the properties of waves is diffraction, and this is where waves spread out to the edges or diffract when they pass through a gap or go past an object. For water waves, we can see the diffraction happening here. When the gap is bigger than the wavelength, we don't get much diffraction. But as we decrease the gap, there is much better diffraction, until the gap is equal to the wavelength when we get maximum diffraction. It should be rather obvious that we could increase the size of the wavelength, leaving the gap size the same, and that would also lead to improved diffraction. Just get the gap size equal to the wavelength. And a practical use? Yes. If you live near a big hill, you might have problems getting TV or radio receptions as the waves are being blocked by the hill. But because of diffraction, the waves spread out when they pass the hill. However, you might just miss the short wavelength signals, but you will get the long ones. And now interference. Interference occurs when two waves merge. The result can be a much larger wave, a smaller wave, or no wave at all. Interference is an import of the principle of superposition. According to the principle, overlapping waves add algebraically to produce a resultant wave or net wave. In other words, when any number of waves meet simultaneously at a point in a medium, the net displacement at a given time is the algebraic sum of the displacements due to each wave at that time. For example, let us consider two waves traveling together along the same stretched string in opposite directions and pass through each other and move on independently as shown on the screen. Each picture depicts the resultant waveform in the stream at a given instance of time. The principle of superposition of waves implies that the overlapping waves do not in any way alter the travel of each other. The amplitude of the resulting pulses is the sum of the individual amplitudes of the individual pulses. If the resulting pulses have zero amplitude, then the pulses are said to have undergone complete destructive interference. Constructive interference occurs when the resulting amplitude is bigger than that of individual pulses. Let us see some interference in water waves. If this guy generates waves from a single point, all we get is a series of circular waves. Nothing interesting there. But if we have two sources of waves, then we get some interesting patterns. This pattern is created by ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's constructive interference. But where the peaks from one wave meet up with troughs from the other, then we get destructive interference, and there's practically no wave there. Interference in light waves. The debate on whether or not light is a wave had been there, and for long, scientists could not strike a common ground. Sir Isaac Newton had suggested that light was a stream of particles. So if Newton's suggestion was indeed right, then a beam of light through two small holes would produce two bright spots on the screen behind it. But it doesn't happen that way. The idea that light is indeed a wave was demonstrated by Thomas Young in 1801. This was the setup. Light was made to pass through a slit S0. The waves emerging from this slit was made to pass through two parallel slits S1 and S2. These two slits served as a pair of coherent light sources because waves emerging from them originated from the same wavefront and therefore maintained a constant phase relationship. Young observed the light from S1 and S2 produced on a screen behind a visible pattern of bright and dark parallel bands called fringes. In reality, this is what the bands look like. But why is that? The same thing with water waves. Because light is a wave from one source can interact with another wave from a different source. When light from one slit met up peaks with peaks or troughs with troughs, they constructively interfere and produce a bright spot. But if troughs from one source interact with peaks from the other, they destructively interfere and there is no wave here. We get dark spots. It's light cancelling itself. The same fate would befall sound. Sound is also a wave and as such suffers interference either constructively or destructively. So if these two speakers are producing sounds with equal vibrations or frequencies, we will get the pattern of waves like this. This is one of the speakers. And if you think of the other, the pattern will be more or less the same. So this is the pattern of interaction that we get. So you see we have points of constructive as well as points of destructive interference. And if you walked along the patterns, you might hear changing frequencies of sound as you get from points of interference to points of destructive interference. Fantastic. Stationary waves. A stationary or standing wave is formed when two equal progressive waves traveling in opposite directions are superposed on each other. This happens, for example, in stringed instruments. When the instrument is played, a transverse wave travels along the string. At the fixed end of the string, the wave is reflected back. The two waves traveling in opposite direction along the string then combine or superpose to form a stationary wave. To produce longitudinal stationary waves, we have a slinky spring that is attached to a speaker that's driven by a power amplifier. So we are going to run it at different frequencies, and when the speaker vibrates, it's going to set up longitudinal waves on the spring. But because the spring is fixed at the top end, these waves will be reflected back. So the incident and reflected waves will superpose, creating a stationary wave. The string will then vibrate in a series of equal segments. If I bring this paper down, I see it bounces a lot until I get to a kind of a stationary point or a point at rest. This is called a node. Where vibration is maximum, that's called an antinode.
So, node, antinode, and there's actually another node down here.
If you keep changing the frequency, you change the node-antinode pattern. We can record the vibrations with this kind of an instrument called an oscillogram. The vibrations strike the diaphragm on the left. They are then recorded as a graph. Now imagine we have another oscillogram and it's recording the reflected vibrations. We would have a pattern like this. This is a stationary wave. In the stationary wave, some points marked N are always at rest. These points are called the nodes. At points marked A, halfway between the nodes, the string is vibrating with a maximum amplitude. These points are called the antinodes. If lambda is the wavelength of the wave traveling along the string, the distance NN or AA between successive nodes or antinodes is lambda over 2, and the distance NA between a node and the nearest antinode is lambda over 4. For two progressive waves traveling in opposite directions to form a stationary wave, they must have the same speed, same frequency, same or nearly equal amplitude. Now, different musical instruments produce sounds of totally different quality, even when played with the same basic frequency or the same pitch. Vibrating string. The frequency of a vibrating string depends upon the material it's made of and the tension and length. When plucked, the string interacts with air particles around it, setting up a longitudinal wave of equal frequency. A transverse wave is set up and can be detected as sound of a given note. A vibrating string exhibits different stationary waves depending on where it has been plucked. To understand this, let us observe this string. Here there is no motion at this endpoint. The string vibrates along its full length and produces its longest possible wavelength. This is the lowest fundamental of the string, sometimes called the first harmonic. If the string vibrates in two segments, it produces a wavelength half the fundamental. This is the first overtone, also called the second harmonic. Given the frequency is proportional to wavelength, its frequency is twice that of the fundamental. When the string vibrates in three segments, it produces its second overtone, the third harmonic. Here the frequency is 3 times that of the fundamental. But usually several modes of vibration occur simultaneously. The result is a compound wave form. Here we represent the fundamental tone supplemented by its first and second harmonics. Differences in the audible components of a sound determine its quality. Quality helps us recognize the characteristic sound of various musical instruments. From that, let us have some definitions. Fundamental frequency, F0. This is the lowest frequency that can be obtained when a musical instrument is played. A stationary wave in its simplest form possible produces a fundamental note which gives the sound from the instrument its basic pitch. Different musical instruments thus have different fundamental notes. The tuning fork produces pure note. Overtones. Many musical instruments, when played, produce a fundamental note accompanied by other notes smaller in amplitude but of higher frequency than the fundamental. These notes are called overtones. It is the overtones that determine the quality of sound. When notes of the same pitch are played on different instruments, they sound differently because of different overtones produced. Sound from a tuning fork is said to be pure because it has no overtones, and that is why a tuning fork is used to tune other musical instruments. The first, second, and third higher frequencies above the fundamental notes are called the first, second, and third overtones respectively. Harmonics. This is the name given to a note whose frequency is a whole number multiple of the fundamental frequency. Frequencies F0, 2F0, 3F0, and 4F0 are the first, second, third, and fourth harmonics respectively. Harmonics should not be confused with overtones, which are also multiples of the fundamental frequency, because it is possible to produce overtones without harmonics. Modes of vibration. For all types of vibration, the ends of the string are fixed to produce displacement notes. The antinodes and the number of loops formed depend on the point where the string is plucked. Fundamental frequency, or the first harmonic. When the string was plucked in the middle, it produced the simplest possible stationary wave. The distance between the two nodes, L, is equal to half the wavelength of the sound wave produced. Therefore, L is equal to half lambda, and thus lambda is equal to 2L. But then V is equal to F lambda, where V is the speed of the transverse wave along the string. Therefore, F0 is equal to V over lambda, which is equal to V over 2L. This is the expression for the fundamental frequency. First overtone, or the second harmonic. This is obtained by holding the midpoint of the vibrating string and plucking the string at a point a quarter of its length from one end. L is equal to lambda 1, where lambda 1 is the wavelength of the first overtone. Since F is equal to V over lambda, the frequency of the first overtone, F1, is equal to V over lambda 1, which is equal to V over L. But then F0 is equal to V over 2L, and F1 is equal to V over L. Dividing the two equations, F0 over F1 is equal to L over 2L, which is equal to a half, and hence F1 is equal to 2F0. This is the second harmonic. Second overtone, or the third harmonic. This is obtained by plucking the string in the middle while touching the string 1/3 of the wave from one end. The waveform obtained is as shown on the screen. L is equal to 3 lambda 2 over 2, where lambda 2 is the wavelength of the second overtone. Lambda 2 is equal to 2L over 3, and hence F2 is equal to 3V over 2L. Dividing equation 1 by 3, F0 over F2 is equal to a third, and therefore F2 is equal to 3F0. This is the third harmonic. It therefore follows that the nth overtone is given by Fn is equal to n plus 1 into F0. Vibrating air columns. A closed pipe. When air is blown into a closed pipe through the open end, the vibration produces a longitudinal wave which travels along the pipe and undergoes a reflection at the other end. The reflected wave then interferes with the incident wave to form a stationary wave. End X must be a node because air at this point is not moving. The stationary wave formed is of the simplest form and the node produced is the fundamental. And L is equal to a quarter lambda naught, so lambda naught is equal to 4L. But V is equal to F naught lambda naught. Therefore, F naught is equal to V over lambda naught, which is equal to V over 4L. This lowest frequency is also the first harmonic. Since the antinode may not form exactly at the end of the pipe, an end correction E is added to L, and thus F naught is equal to V over 4 into L plus E, where E is the end correction. First overtone. When air is blown more strongly into the pipe, overtones which are multiples of the fundamental frequency are obtained. The open end is always an antinode while the closed end is a node. From this, L plus E is equal to 3 over 4 lambda 1. But lambda 1 is equal to V over F1. So L plus 1 is equal to 3V over 4F1. Hence, F1 is equal to 3V over 4 into L plus E. But then F0 is equal to V over 4 into L plus E. Therefore, F1 is equal to 3F0. The frequency of the first overtone is thrice the frequency of the fundamental. It is the third harmonic. Similarly, it can be shown that the frequency of the second overtone is 5 times the fundamental frequency. It is the fifth harmonic. In the same way, third overtone F3 is equal to 7F0. Fourth overtone F4 is equal to 9F0. The nth overtone Fn is equal to 2n plus 1 into F0. It follows therefore that a closed pipe produces only odd harmonics. A vibrating string produces more quality sound than a closed pipe when it has all the harmonics. Finally, an open pipe. When air is blown, the stationary wave formed has antinodes at both ends because air is free to move. The simplest type of wave which gives the fundamental frequency is as appears on your screen. Now L plus 2E is equal to a half lambda naught. But lambda naught is equal to V over frequency naught. And therefore the fundamental frequency is given by F0 is equal to V over 2 into L plus 2E. First overtone. From the figure on your screen, L plus 2E is equal to lambda 1. But lambda 1 is equal to V over frequency 1. And therefore, frequency 1 is equal to V over lambda 1, which is equal to V over L plus 2E. And hence, F1 is equal to 2F0. The frequency of the first overtone is twice the fundamental frequency. It is the second harmonic. It can be shown in the same way that the frequency of the second overtone, F2, equals to 3F0. Similarly, third overtone, F3, is equal to 4F0. Fourth overtone, F4, is equal to 5F0. The nth overtone, Fn, is equal to n plus 1 into F0. Thus, an open pipe has all the harmonics, that is both even and odd.
When thinking about your career and wondering what to study to equip yourself for the working world, MSc is the college to help you make this decision. We have 23 campuses nationwide and a wide range of aligned and accredited programs to choose from. Best of all, easy payment terms and flexible class times. MSc College is your ticket to a better life. Call 0860 672 265 or visit msccollege.co.za.